Okay, hello, it's Tyler Unuzzi, and we're going to evaluate the electrical potential between two spherical shells, as we can see here. So, I drew this diagram in prep just so I didn't have to draw it out and explain it, but I'll explain it now. And so essentially what we have here is we have a metallic spherical cell with positive Q charge that's distributed throughout, and then we have another shell on the outside that has negative Q charge that's distributed throughout. And it's distributed throughout because they're both metals. From the point in the center, there is a radius of A to the inner shell, and then a radius of B to the outer shell. And then we drew in a Gaussian surface, and we gave that a radius R. And then we have all these lines radiating outward as a direction of our charge. So now we're going to evaluate the potential difference, but to do that first, we need to begin with finding the electrical field of this system. And to do that, we can start with Gauss's law, which is the path integral of E, the electrical field, and the surface area of the Gaussian surface, which equals the Q enclosed over epsilon naught. So the surface area of our Gaussian surface is simply the surface area of the sphere, and we know that to be 4 pi r squared. So with that established, we can then plug this in to here and replace that, and then we'll be able to move into our next step. Also, we can drop the vectors above each of these two variables because it'll be traveling in the same direction as the area. So it'll be going this way, which means it's parallel, and therefore the normal, which is in here, which you could replace it with the normal n hat, which you could replace that with, essentially goes to 1. And then simply we can just write it as a product. So to do that, we just plug in our area, which is here. We'll keep the E, because we're going to solve for that later. And then we'll plug in 4 pi r squared. The r squared comes from the radius that are Gaussian surfaces. Just want to remind you of that. And then we'll keep our Q enclosed and epsilon naught. So as of right now, we can look at the charge enclosed by the Gaussian surface, which is simply Q plus Q, and we'll just leave that as simply Q. So now if we replace that and then solve for the electrical field, we will yield 4 pi epsilon naught over 1, and then we'll leave it as Q over r squared. So now we have the electrical field, and we solve for that, and now we're going to look at the potential difference. So we can look at the equation which is on our equation sheet, and this reads as the potential difference is equal to the negative integral of the electrical field and then the distance as a vector. So we'll just quickly write that out, and our change of potential is therefore equal to negative integral E vector dot product dr vector. And then what we're going to be able to do is actually replace the dr with ds, and our ds is going to look at simply just the same thing, but we're just going to replace it, and this will allow us to then still look at the potential difference. But now we can know that since the electrical field and the ds are going to actually be perpendicular, we're going to go in opposite directions, my apologies. So then we know it's going to be a negative E ds. And we can drop that product. And then we're going to write this more clearly as just the integral from the negative plate or negative charged space to the positive charged space, and then we're going to keep the E ds. And we'll just leave this as a positive and keep in mind that the this is negative. So now we are ready to look at, we're ready to replace E into our equation. So this is coming all the way down here. And we can rewrite this as the change potential is equal to, and I'm going to quickly rewrite that since our negative charged surface is out here, we'll put B in for the distance, and then since our positively charged surface is in here, we'll put A up top. And now, like I said, we can replace this in, and I'm actually going to rewrite it a little bit just so we'll keep with respect to one thing in particular. And I'm going to rewrite this as Q of the 4 pi epsilon naught. And then going to put in multiplied by 1 over r squared. And now I'm going to integrate this with respect to dr. And we want to integrate with respect to dr because we're going from here to here. So we're moving from the point in the middle to here, which is the radius. So we want to, with respect to dr. And then this will actually come with a negative as well because of our path of integration goes against it. So because that path of integration goes towards the negative direction, we actually have to take a negative, but I'm going to immediately pull the negative out up front here. And now I'm going to pull out the constants. So our constants are actually the Q, because the charge enclosed will remain the same. And then all of this at the bottom is always constants. So we can just rewrite this as the change potential equals negative, keep that negative sign, don't lose track of it, Q 4 pi epsilon naught. Let's see, integral B to A, and then we'll just leave it dr over r squared. And now we can evaluate the integral to find the potential difference. So if we evaluate the integral and we plug in our negative, I'm just going to skip over those steps since it's algebra. It's essentially just taking the integral of 1 over r squared, which will become, if you take the integral of an r squared, you'll get r to the negative squared, and then plus 1, and then you divide by that negative 1. So what happens is they actually kind of flip-flop, but then they're going to flip-flop back because we have this negative over here. So it'll end up becoming this, which is the charge, 4 pi epsilon naught, 1 over A minus 1 over B. So now we can actually, we don't have to distribute, but we're going to rewrite this, which is inside the parentheses, but we're not going to distribute this, we're just going to leave this to the outside. But we're going to essentially just create a product over here and a product over here. So to do that, we're going to get change in V equals Q 4 pi epsilon naught B minus A over AB. And essentially what we did is we just did A times A, or A, BB, and then AA, which is just getting them so they have a common denominator and then putting them together. And then this will essentially be our final answer, which is the change potential equals the charge divided by 4 pi epsilon naught multiplied to the quotient of B minus A over AB. And essentially that is all we have to do to get the potential difference between two surfaces, two spherical surfaces, using an electrical field, Gauss's law, finding the electrical field first, and then setting up our integral for the change of potential, and then plugging in our electrical field into there to then yield an integral which we can then solve and find our final equation. So this is for the spherical potential difference.